All right, this is the CSIG Weekly Talk series of cognitive topics, and I'm going to hand over to Vijay and Minh to speak about phonetic matching techniques for voice-based information retrieval. Over to you, Vijay.
Thanks. Yeah, so good morning, everyone, or good evening, wherever you are located. I'm Vijay Ramakrishnan. I'm in the MindMeld team within Cisco. So we develop voice assistants for Cisco's endpoints, and I am a machine learning engineer there. And my colleague, Minh, is in the same organization. This presentation and the technology is in collaboration with my team. So this includes Arushi, Varsha, Lucian, and Karthik. And the title of this presentation is Phonetic Matching Techniques for Voice-Based Information Retrieval. So as an introduction, where this entire technology lies is in this little component called the entity resolver. So before we talk about the entity resolver, I just want to give a quick overview of what it takes to build a voice-based AI assistant. So traditionally, you have a device, and this device communicates with an automatic speech recognition service. It could be on the device itself, or it could be on the cloud. And so once you communicate with that, the ASR device or the component would then transcribe it into a sequence of characters. This sequence of characters then communicates with the assistant. So everything from here is the assistant. And some of the main components of the assistant are the natural language processor, the question and answer, the dialogue manager, and the application manager. Specifically, the natural language processor has a bunch of components. One is a bunch of classifiers. So a classifier in this case would be classifying the intent of the input query. So for example, good morning would be classified as the greetings intent. We also have something called the entity recognizer. And traditionally, the entity recognizer, you're trying to extract spans of tokens within your input query, and and these spans of tokens are tokens of interest to your organization. Once you extract the entities within a query, you want to resolve the canonical names of those entities. So for example, if I say something like, good morning, Vijay Ramakrishnan, the entity of interest, at least for this application, would be Vijay Ramakrishnan, because that's the name of a person that I'm trying to communicate with. Once I extract that entity, I need to resolve that entity to a business object within my knowledge base. And this business object could have various fields, for example, the employee ID of Vijay Ramakrishnan. So this entire presentation will be talking about how you resolve the entity into a canonical name within your business organization. And that's what the entity resolver actually does. So let's dive a bit deeper into this component itself. So entity resolution or entity linking is a classic natural language processing problem of disambiguating the terms. So for example, in this text, you have Michael Jordan is an American scientist, et cetera, You can have different candidate entities for that. So it could be Michael J. Jordan, the basketball player, Michael I. Jordan, Michael W. Jordan, so on and so forth. And based on the context, as well as who is speaking and other context information, you can disambiguate it to Michael I. Jordan based on all the text following that term. There are various methods of actually doing entity linking or entity resolution. There are clustering techniques. You can do classification models, deep neural networks, and information retrieval systems. In this presentation, we'll be talking about information retrieval-based approaches to this entity resolution problem. But like I mentioned, there are other techniques out there that can be used. So traditionally, information retrieval is done for text inputs. And by text inputs, what I mean is you're typing something on a keyboard or a smart device or whatever. And based on that input, those characters would have some characteristic types of errors. So one such type of error is fat finger typos, spelling errors, abbreviations, special characters, and so on. So an example would be pumpkin latte is the input query that someone typed. And obviously over here, you're missing the P in the pumpkin. And you need to resolve that into pumpkin spice latte, which is the business object within your knowledge base. Some techniques that you can use here are fuzzy matching, character engrams, token engrams, and based on that, you can match these and then get to the right resolution of the object. There's other challenges. So you have syntactically different but semantically similar terms. And what that means is, as you can see in the example, spaghetti marinara, which is the canonical object, has to be matched with pasta with tomato sauce. So in order to do this resolution, you need extra features. So in this case, you can have a list of synonyms. And the synonym list here would be the list of ingredients to make spaghetti marinara. And once you have the ingredients list, you can sort of match that against your input query and then hopefully get spaghetti marinara as the match. You can also disambiguate based on outside context. So for example, She Will Be Loved, which is an album, can be matched to She Will Be Loved by Maroon 5 or She Will Be Loved by Corey Gray, who are two different artists. And one way to do this is by looking at the preferences of the user who is saying it, and based on the history of the music that they have been playing or whatever, you can basically match one or the other. So this is more on the context side of things. So this is what traditional systems actually do. Voice is different. And the reason why voice is different is it has more sources of errors. These errors are noisy environments as well as variations in accents and pronunciations. People are speaking around you, and there are different accents of people. And so the ASR system has to handle all these different variations. Moreover, in production systems, your automatic speech recognition models are black boxes in the sense that you cannot access some of the hidden layers within the model. And so essentially you have to work with the quirks of that particular ASR model. There are higher likelihoods of propagating errors. So like I mentioned previously, you have a bunch of classifiers like the entity classifier before you can resolve the entity. And so if you have the wrong intent or domain, or your entity gets classified wrongly, then that would cascade all the way to entity resolution because you just haven't gotten the right span of tokens to classify. So that's the other issue. Text similarity is not always a good proxy for phonetic similarity. So you might be thinking, you could just take this ASR mistranscribed text and sort of do character edit distance and then match it against your internal corpus of, business objects. But that really doesn't work because here's an example. You have a gold name that you're trying to pronounce. In this case, it's Minh, who's my colleague. The ASR transcribes that into Mentos. And, if you just use typical edit distance, Levenstein or whatever, you would, Mendoza would match closer to Mentos than Minh. And so you don't want to really use character edit distance most of the time. You want to use other phonetic matching signals to capture this closeness. And we'll be talking about that more in the latter half of the presentation. However, if the token is transcribed correctly, if Minh was transcribed correctly to Minh in the ASR, then you want to use text similarity. So it has to be a balance between phonetic similarity and text similarity for voice-based input. And finally, there's a lot more challenging feedback loops in voice versus text. Because in text, if you get something wrong or a character wrong, you can always correct it by typing it again. But for voice, you can't really correct it because the ASR system could just be biased against your accent. And so you can repeatedly say the same things, but it would always systematically classify what you say incorrectly. And so that's why it's a bit harder to actually work with ASR versus traditional text-based inputs. So before we talk about some of the techniques that we use, I just wanted to give a very brief overview of how ASR works. The input features that you traditionally get into these ASR systems are frequency-based features like MFCCs or MEL frequency septal coefficients. Then you have this transformation from the audio features to aligned phonemes. And this is normally done using a deep neural network like an RNN, recurrent neural network, or a convolutional neural network, depending on the type of use case that you have. And then finally, you have a language model that then ranks multiple sequences of strings based on how probable that sequence of string is in a given language. So maybe good morning, Vijay is more probable than some sort of mistranscription of good morning. So you finally have this language model that then ranks multiple hypotheses. So the types of errors that we have observed in voice-based assistants are as follows. So ASR mistranscription leads to NLP misclassification. So an example would be, I'm trying to say the query, get me on a line with Omid. Omid is the name of a person. The prediction of the ASR is, give me an alarm with Old Maid. And so when you run give me an alarm with Old Maid through an intent recognition classifier, you would get a completely different intent compared to what you actually wanted, which is call person intent. So one way to solve this is by adding such kinds of systematically noisy data into your classifier's training data. So this would involve developing more powerful classifiers. And we have used conditional random fields to work with some of this noisy data in our classification. Some of the phonemes are just not recognized. So for example, let's get a hold of Mahojwal. In this case, the ASR completely butchers the last few characters. So let's get a hold of my jaw, and wall is completely taken out. For these types of errors, you can use phonetic matching techniques that I'll be discussing. The language model also incorrectly biases to common vocabulary words. So call Navjot for me gets mistranscribed as download YouTube for me. And the reason why this happens is because download YouTube is just a much more stronger sequence of words compared to call Navjot, just because Navjot is just a very rare term within the ASR vendor's language model. And this can also be corrected using information retrieval techniques. The ASR model itself mistranscribes to similar phonetically but textually different tokens. So if your input is, can you connect me with Kiran Prakash, the ASR transcribes that into, can you connect me with Corinne Precautious. Kiran Prakash and Corinne Precautious are phonetically sort of similar, but obviously from a character edit distance standpoint, they're quite different. The entities are mistranscribed to other entities. So in this case, it's quite standard. Can you call Didi gets mistranscribed to can you call Stevie? And so you might have Stevie as already a name that you want to match against. So again, you can sort of do phonetic matching techniques to recover this error. The context and entity tokens can be fused. So connect me with Heather gets mistranscribed as connect Merriweather. So over here, you would have to use more advanced entity recognition classifiers, where you would essentially have to classify, at the middle of this word as weather to be matched with Heather. Otherwise, you will get Mary also matched with weather, and that is too much of characters that you want. And finally, some of the non-entity tokens can be mistranscribed. So when you say join Marvin's PMR, sometimes it gets mistranscribed into John Martin's PMR. And so John Martin is also a name, but join gets converted into John. You can also recover from this using advanced entity recognition techniques. And we won't be talking about those here, but I just wanted to specify some of the solutions that are available for such types of mistranscriptions. So let's go through some of the phonetic encodings that are available and what we use. So traditional phonetic information retrieval techniques are solving the problem of finding names in the corpus, which is sort of what we want to do in our internal architecture. We also want to match against names. And so this is a good start. And what these techniques do is they map arbitrary name strings into fixed length string representations. And so similar sounding names map to the same representation, or hopefully they match to the same representation. The oldest technique is SoundX. And what SoundX does is that it's a rule-based system. And by rule-based, what I mean is it's a bunch of case statements. And based on these rules, it transforms the input to a single letter and 3 digits after that. So one example rule is retain first letter and drop all other vowels. The limitation of Soundex is that it's only US based and it considers only English pronunciations. And it's also mapping a large space to only 4 characters. So you have issues like a lot of high false positives. For example, Hilbert and Heilbronn are mapped to the same Soundex representation. And they don't really sound that similar. And so ideally, they shouldn't be mapped to the same representation. The other technique is metaphone. It's more sophisticated, but it's still rules-based. It's more efficient than Soundex from a computational standpoint. And the limitations here, again, it's mostly focused on English pronunciations, and it has high false positive rates. What we use is double metaphone, which is an iteration of metaphone. It's more complex rules, essentially. But it has support for more languages. So you have support for Chinese, Romance, and Slavic languages. So for mistranscriptions of those types of names, they can sort of be corrected using matchings from double metaphone. It returns 2 transformations. One is the primary code, which is how the native speaker would pronounce a particular name. So for the input Cabrillo, your encoding would be Cabrillo. Sorry, that would be the secondary encoding is what the native speaker would pronounce it as. And the primary one is what an English speaker would pronounce it as. So in this case, it would be Cabrillo. So again, I've given an example down below. Smith gets mapped to SM0 and XMT, and Schmidt gets mapped to XMT and SMT. So by using the primary and the secondary codes, you can match against one of them and hopefully get Smith and Schmidt close together. There's another iteration of double metaphone, which is Metaphone 3. It's a commercially available software only, so we don't use it in our systems. The other technique that we used is grapheme to phoneme conversion. A grapheme here is, you can think of it as just a character within a language system. A phoneme is a basic unit of pronunciation. And what G2P is trying to do is it's trying to generate the pronunciation phonemes of a generic set of words. The traditional way that this has been done is you create and maintain a large pronunciation dictionary. So this dictionary would have the key as a particular word and the value as the phonetic representation of that word. The problem with this system is that if your word is not in this dictionary, you're out of luck. And so it doesn't really work out for us because names are in this huge representation space. A name could potentially be any combination of characters. So this approach doesn't really work. There's another approach that we used, which is quite interesting, which is CMU Sphinx. And what CMU Sphinx does is that it does have this, this huge mapping from grapheme to phoneme. But you can train a sequence-to-sequence deep learning model that learns new phoneme representations of unknown words. So by looking at the statistical patterns of this corpus, you can essentially put in a new input of graphemes and get an output that is the phonetic representation of it. So you can think of it as a standard machine learning, machine translation based model, but applied to grapheme to phoneme. So some drawbacks of phonetic matching are as follows. As I mentioned, you get these surprising results for users Hilbert and Heilbronn. Even in the G2P, there are some errors. So Josette gets mapped to the pronunciation of Josette. So it's not really the same. And so some of these errors can compound just because you have issues with your ASR, with the language model, and finally your phoneme transformation. So talking about our architecture itself, we trained a sequence-to-sequence model, like I mentioned before, using an LSTM with attention. We used 3 hidden units and 64 units per layer, and this was built in TensorFlow. In order to really speed up the transformation process, we use a cache that just stored some of these transformations that we already use, and then just looked it up based on if someone says it again. For the knowledge base, so we also had to create this knowledge base of all the phonetic transformations of proper nouns in our database. So in this case, we wanted to use names within a company, and we took the character and phonetic representations of these names extracted them, encoded, and stored them in a knowledge base. The knowledge base that we use here is Elasticsearch. In addition to traditional character and word alignments, the following phonetic alignments were also used. So one thing was G2P. And the way that we use G2P is that we use this external sequence-to-sequence system to map the name to the phoneme. And then we tokenize that phoneme. So we took 2 grams all the way to 4 grams of those tokenized phonemes and stored them in this knowledge base. For double metaphone, this was natively supported by Elasticsearch, so we actually didn't have to do much. We did introduce some fuzziness so that even if though your double metaphone didn't match exactly, it would still match because there was some fuzziness involved with the matching property. So we're talking about the experimental methodology that we used in order to test our system. We gathered names from the US Census, so this was about 20,000 names. Then we crowdsourced different ways that people did a specific task. In this case, it was a collaboration-related task. So how do you call a friend using Siri? And then we slot-filled the names within those action statements that we crowdsourced. And then we crowdsourced the slot-filled statements and asked the user to essentially record them saying that. Then we took the recordings and then we ran that through an ASR vendor. And so we transcribed that. And then we evaluated our systems against just people saying names versus people saying names and the collaboration task-specific context. So can you call Vijay Ramakrishnan is one example of this task-specific transcription, versus a name would just be like Vijay Ramakrishnan, and the user would have to say it. So we collected about 11,000 queries for the names only evaluation set and about 16,000 queries for names plus context. We also did a bunch of hyperparameter tuning. So we ran different versions of the index, and this slide is very specific to Elasticsearch. So people who don't really understand the details of Elasticsearch, I would probably skip over some of these things, but we tried different ways of tokenization, filtering, and using different analyzers in Elasticsearch. We also tuned G2P itself so that we get a better representation of these phonemes. For ranking and tuning, we compared models side by side for the regressions and improvements, and then changed the weights depending on the characteristics of these regressions. And finally, we did some random walk tuning. So we automated, just a basic way of doing hyperparameter tuning is you just automate the search space. So we used the grid search approach with the objective function being recalling the names, the canonical names that are expected. So here's a very short summary of the results that we found for the names only name recall. So the name recall at 5 here means that for the expected canonical name, it has to be in the top 5 results that are matched against our information retrieval system. So if the canonical name is in the top 5, then it's correct. If it's not, it's wrong. And so when I say 50% correct, I mean that at recall at 5, 50% of the queries had the correct canonical name in the top 5 results. So without using G2P, with only using double metaphone, we had about 30% accuracy with the names only database or names only evaluation set. And for names and context, we had about 20%. Using G2P, this improved quite significantly to about 50% for names only and about 30% for names plus context. So just a quick comparison between G2P and double metaphone. For G2P, the cons are that it's less efficient in matching because the latency is very high and it's not standardized in IR systems. But the good thing about it is that you have a higher match rate just because there are more number of tokens that you can match against. Double metaphone is more efficient. It's very efficient because it's natively implemented in these IR systems. But you have a lower match rate just because you only have 4 characters that you need to represent. And so there's not much overlap. And it's not extensible, versus in G2P, you can add new training data and get better results over With that, I'll end my presentation and open it up for questions.
Oh, there are lots of questions. Lots of questions. Is S the S sound, or how is silence and timing shown in the phonetic transcript?
How is silence and, sorry, let me, okay. Okay, I'm not referring to what this is saying, but is the question, how is silence represented in phonetic
Yes.
representations?
Yes.
Okay, so silence is, so we leave the silence part to the ASR vendor itself. So in this case, you would get, the transcription of actual words, and you can tokenize. So anytime you tokenize the word, the space in the between is the silence part. So we don't handle the silence part. We just take whatever the output is from the ASR vendor and then run it through our phonetic function itself. So we don't have to deal with silence. I think that's what the ASR vendor has to deal with. And so you have different types of ways to do that, like CTC loss function and so on. But we don't do that. We don't solve that problem.
Is the system available online somewhere? Any aspects of open access on GitHub?
Yes, so we submitted a paper to EMNLP 2018, so it will be published soon. So once that is published, the details of the analyzers that we used and everything will be there. But
you won't have a GitHub repository?
That's actually a good question. I mean, we have the evaluation set. The actual, yeah, I'm not very sure. I think that's a good question.
Okay, you can think about it. You can pursue.
Yeah.
How to determine if models are biased against your accent? How to correct address?
So so we already know, like some of our ASR vendors, what they are biased against. They're normally biased against Asian names, Chinese and Indian names in particular. And there are some quirks, like I think sometimes some models get it very correct for Indian names, some models are much better for Chinese names. So we try to use a generic approach to solve these problems. So even though the ASR system is biased, we built the entire system such that you can swap out a given ASR vendor with some other ASR vendor, and it should work roughly equally. And the way that we do that is, I think like I explained, double metaphone, for example, is good at matching different types of accents or the representation of different types of accents. So looking at different ways at which the phonetic transformation can be less biased in the sense that it can have more complexity of mapping different accents to the right representation. That's what we rely on. But yeah, we're not trying to solve for a given accent. We're trying to have a generic solution.
Do you use, I think you mentioned you use TensorFlow.
Yeah.
Do you use Onyx in any way? Anything else? Keras, PyTorch, Caffe? But Onyx model exchange format. Do you use any of those?
Yeah, so I think, so for now we're just using TensorFlow. And I think the reason why we're using TensorFlow is that we have a pretty good pipeline set up to optimize the models for model inference. But yeah, like pretty much you can use any system out here because this data is already available. The corpus is already available between your inputs and outputs. So you can essentially train a PyTorch model or a Keras model or whatever, and it should work out of the box. The actual LSTM model itself is available with CMU Sphinx. We made some edits to it in order to get a higher accuracy, but the architecture itself is very similar to what CMU Sphinx is doing.
Any quick questions from anybody? I see references to your work relating to translation. People have given you links to blogs. Jim Sporer has linked to his earlier work in 1980 that may be relevant.
Scott just put a question in.
Oh, Scott.
Hi, Vijay. This is Scott. I'm curious how you would introduce a new data set, for example, of lexemes, which are kind of graphemes, phonemes, such as Wikidata, Wikipedia's lexeme project, and in its 301 languages.
Yeah, this is actually a good question. I we don't have any plans to do this yet. The way that we are currently doing it is we are looking at the output of our model and then seeing what the model is actually giving us in terms of the, like a particular inaccuracy in this transformation process, and then we proactively add those back into the training data. So we don't have any plans of yet, but this is a good reference. This is something that we'll look into.
Love to be more in touch about this. Thank you for your excellent presentation.
Thanks.
Any more questions, anyone? Okay, I don't see any more questions. Thank you for the wonderful session. And the slides are actually on the website already. You can see them there, and the recording will be up later today or tomorrow at the latest. So I'll paste the link to where the slides are. There we go. Okay, I'll stop recording.